So let's start with the supervised learning. Now, supervised learning is another very important kind of a learning in artificial intelligence and machine learning. Now, the topic that we are going to discuss under supervised learning is dimensionality reduction or dimension reduction. It is the transformation of the data from high dimensional space into a low dimensional space. So, what is dimensional reduction? In machine learning classification problem, there are often too many factors on the basis of which the final classification is done. These factors are basically variables called features. You must have seen in the Excel sheet or any database, there are so many columns. Now, all these are sometimes found to be redundant or not extra. So the higher the number of features, the harder it gets to visualize the training set and then work on it. So it is always recommended that try to minimize if possible. Sometimes most of these features are correlated and hence redundant. This is where dimensionality reduction algorithm comes into play. Dimensional reduction is the process of reducing the number of random variables under consideration by obtaining a set of principal variables. It can be divided into feature selection and feature extraction. So you can identify that what are those features or what are those variables which are not essential, not required. Maybe they are kind of redundant. So you can remove them. Now let us try and understand with a simple example. Consider below there's a data, or here we are having weights of similar objects. Now suppose a person is weighed in kgs and he is also weighed in pounds. Now these are two units of measurements. Now both of them are not required, because as far as your understanding is concerned, I think one will do. So if we use both of these variables, they will convey the similar information. So it would make sense to use only one variable. We can convert the data from that 2D x1 and x2 to 1D. So there is no need of having two variables for the same unit. That's how. This is a very simple example, but likewise in the actual data, when you will see, you will find that there are so many variables or features which are not required, which you can minimize them or you can remove them. Similarly, we can reduce p dimensions of the data into a subset of k dimensions. This is called dimensionality reduction. Now, why it is required? Dimensional reduction. Here are some applying dimensionality reduction to a data set. Space required to store the data is reduced. Obviously, when you remove certain variables, the space to that extent would definitely be reduced as the number of dimensions get reduced. Less dimensions lead to less computation, training time also, because definitely your training time will get reduced. Some algorithms do not perform well when we have a large dimension. Now this is a very important factor. That is, if sometimes just because the number of dimensions that you have, number of features that you have, there are so many that you find it difficult. And the system finds it difficult to perform any operation in a very least possible time. So reducing these dimensions need to happen for the algorithm to be useful. It takes care of multi-collinearity by removing redundant features also. So that also is a very important aspect. For example, you have two variables, time spent on treadmill in minutes and then calories burned. Now these variables are highly correlated, as the more time you spend running on a treadmill, the more calories you will burn. So hence there is no point in storing both, as just one of them does what you want to do. It helps in visualizing data also. Now, as discussed earlier, it is very difficult to visualize the data in higher dimensions. So reducing our space to 2D or 3D may allow us to plot and observe patterns more clearly. So there are various reasons for this. So dimensional reduction is a very useful option available so that you can get your job done as quickly as possible. Now, components of dimensional reduction. There are two components of dimensional reduction, that is feature selection. In this, we try to find a subset of the original set of variables or features to get a smaller subset, which can be used to model the problem. It usually involves three ways, that is filter or wrapper or embedded. Feature extraction is this reduces the data in a high dimensional space to a lower dimensional space, that is a space with a lesser number of dimensions or features. Now methods of dimensional reductions are various methods used for dimensional reductions are PCA, that is principal component analysis, linear discriminant analysis, generalized discriminant analysis. Now dimensional reduction may be both linear or non-linear depending upon the method used. Let us first discuss principal component analysis, which is the most popular and common method. PCA, this method was introduced by Carl Pearson. It works on a condition that while the data on a higher dimensional space is mapped to data in a lower dimensional space, the variance of the data in the lower dimensional space should be maximum. So that is how this works. It involves the following steps, that is construct the covariance matrix of the data, compute the eigenvectors of this matrix. Eigenvectors correspond to the largest eigenvalues are used to reconstruct a large fraction of variance of the original data. And what is eigenvector? Let's try and understand that also. Eigenvector is the factor by which the eigenvector is scaled. That is geometrically an eigenvector corresponding to a real non-zero eigenvalues points in a direction in which it is stressed by the transformation, and the eigenvalue is the factor by which it is stressed. So that is the eigenvalue, and then vector is in the direction in which you are going to stretch it. Hence we are left with the lesser number of eigenvectors, and there might have been some data loss in the process. That is a possibility. But the most important variances should be retained by the remaining eigenvectors. Now note that an eigenvector is a vector whose direction remains unchanged. Because of it is a vector, the direction remains unchanged when a linear transformation is applied to it. And eigenvectors are a special set of vectors associated with a linear system of equations. And eigenvalues are a special set of scalars associated with a linear system of equation, that is a matrix equation, that are sometimes also known as characteristic roots. Now advantages of dimensional reduction: it helps in data compression and hence reduced storage space. It reduces computation time. It also helps remove redundant features. Some disadvantages, like it may lead to some amount of data loss. PCA tends to find linear correlation between variables, which is sometimes undesirable. PCA fails in cases where mean and covariances are not enough to define data sets. We may not know how many principal components to keep in practice. Some thumb rule are applied in this. Now let's try and understand principal component analysis. Now principal component analysis is the process of computing the principal components and using them to perform a change of basis on the data, sometimes using only the first few principal components and ignoring the rest. Now it depends on the situation, how you want to take it. Large data sets are increasingly common and are often difficult to interpret. Principal component analysis is a technique for reducing the dimensionality of such data sets, increasing interpretability, but at the same time minimizing the information loss. It does so by creating new uncorrelated variables that successively maximize variance. Now, in order to interpret huge data sets, methods are required to drastically reduce their dimensionality in an interpretable way, such that most of the information in the data set is preserved. So that is the objective, so that the loss in the data should be as minimal as possible. Many techniques have been developed for this purpose, but principal component analysis is one of the oldest and most widely used. Its idea is simple: reduce the dimensionality of the data set while preserving as much variability, that is statistical information, as possible. Now, factor analysis is another very important subtopic of this. Factor analysis is a technique that is used to reduce a large number of variables into fewer number of factors. Factor analysis is an exploratory data analysis. You have to explore, you have to go deep into this. And this method is used to search influential underlying factors or latent variables from a set of observed variables. It helps in data interpretations by reducing the number of variables. It extracts maximum common variables from all variables and puts them into a common score. Now, factor analysis is widely utilized in market research, advertising psychology, finance, and operation research. Market researchers use factor analysis to identify price-sensitive customers, identify brand features that influence the consumer choice, and helps in understanding channel selection criteria for the distribution channel. Factor analysis is a linear statistical model. It is used to explain the variance among the observed variable and condense a set of observed variable into the unobserved variable called factors. Observed variables are modeled as a linear combination of factors and error terms. Now, factors or latent variables is associated with multiple observed variables who have common patterns of responses. Each factor explains a particular amount of variance in the observed variables. It helps in data interpretation by reducing the number of variables. Factor analysis is a method for investigating whether a number of variables of interest x1, x2 up to, and it goes on, x1 are linearly related to a smaller number of observable factors f1, f2, and like that up to fk. Observed variables and factors. So you can see that there are so many variables which are there, and you can minimize it, condense it, or remove them, and then make from out of 3 only 1, out of 3 again 1, and like that you can go on minimizing it. That means you are reducing the dimensions of that. Assumptions: there are no outliers in data. Sample size should be greater than the factor. There should not be perfect multicollinearity. There should not be homoscedasticity, means that given a set of data, any two subsets will have a similar level of variance between the variables. Types of factor analysis. Exploratory factor analysis. It is the most popular factor analysis approach among social and management researchers. Its basic assumption is that any observed variable is directly associated with any factor. Confirmatory factor analysis. Its basic assumption is that each factor is associated with a particular set of observed variables. CFA confirms that what is expected on the basic. How does factor analysis work? The primary objective of factor analysis is to reduce the number of observed variables and find unobservable variables. These unobserved variables help the market researcher to conclude the survey. This conversion of the observed variables to unobserved variables can be achieved in 2 steps. Factor extraction. In this step, the number of factors and approach for extraction selected using variance partitioning methods such as principal component analysis and common factor analysis. Factor rotation. In this step, rotation tries to convert factors into uncorrelated factors. The main goal of this step is to improve the overall interpretability. There are lots of rotation methods that are available, such as Varimax rotation method, Quartimax rotation method, and Promax rotation method. So depending on the suitability, you can use that particular rotation methods. Terminology. What is a factor? A factor is a latent variable which describes the association among the number of observed variables. The maximum number of factors are equal to number of observed variables. Every factor explains a certain variance in observed variables. The factors with the lowest amount of variables were dropped. Factors are also known as latent variables or hidden variables or unobserved variables or hypothetical variables. What are the factor loadings? The factor loading is a matrix which shows that relationship of each variable to the underlying factor. It shows the correlation coefficient for observed variable and factor. It shows the variance explained by the observed variables. What is eigenvalue? Eigenvalue represents variance explained each factor from the total variance. It is also known as characteristic roots. What are communalities? Communalities are the sum of the squared leading for each variable. It represents the common variance. It ranges from 0 to 1 and value close to 1. It represents more variance. So this is the formula for that. What is factor rotation? Rotation is a tool for better interpretation for factor analysis. Rotation can be orthogonal or oblique. It redistributed the commonalities with a clear pattern of loadings. Choosing the number of factors, Kaiser criterion is an analytical approach which is based on the more significant proportion of variance explained by factor will be selected. The eigenvalue is a good criterion for determining the number of factors. Generally, an eigenvalue greater than 1 will be considered as selection criteria for the feature. Now, the graphical approach is based on the visual representation of factors, eigenvalues, also called scree plot. The scree plot helps us to determine the number of factors where the curve makes an elbow. So you can see on this graph that this graph is known as a scree plot, and you can see it's a elbow shaped graph. So which means that it gives you that what are the factors which are having the curve, and those factors will be selected. For analysis versus factor analysis versus principal component analysis, PCA components explain the maximum amount of variance, while factor analysis explains the covariance in data. PCA components are fully orthogonal to each other, whereas factor analysis does not require factors to be orthogonal. PCA component is a linear combination of the observed variable, while FA, the observed variables are linear combination of the unobserved variable or factor. PCA components are uninterpretable. In factor analysis, underlying factors are labelable and interpretable. PCA is a kind of dimensionality reduction method, whereas factor analysis is the latent variable method. PCA is a type of factor analysis. PCA is observational, whereas FA is modeling technique. So that is how you can say that the principal component plays a very important role, and in that, of course, the dimensional reduction and the factor analysis, both of them are very important. So this is your dimensional reduction under the supervised learning. Thank you for the first tutorial to be completed. Thank you.